Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you some important NDVI analysis in the Google Earth Engine platform and Python API programming. At the end of this tutorial, you will be able to plot the NDVI during the growing season, and also you can calculate important criteria in the growing season that helping you to discriminate different crop types over your region of interest. Some parameters like peak NDVI, base NDVI, amplitude, and also start of growing season, end of growing season, and the length of the growing season. For example, here you can see for the same area the length of growing season calculated, and also it's really important information that helping us to discriminate different crops over the entire region. In this tutorial, I'm gonna actually show you one of the new products releasing by NASA available in the Earth Engine, and here you can use a kind of satellite data that is combination between Sentinel-2 and Landsat-8 images that's offering 3 meters spatial resolution and 3 days temporal frequency. It's mentioned daily, but for most of the areas it is available with 3 days temporal frequency. And also this product is really valuable. Same times you have a Landsat spatial resolution and Sentinel spectral resolution and higher temporal frequency, that is 3 days. That is awesome for the crop phenological analysis. So I'm gonna show you how to deal with this product and how to monitor crop variation during the growing season using important metrics that typically we use them for the phenological analysis. If you want to learn how to do this procedure, make a new notebook in the Colab environment and follow this tutorial. In the first step, we need to import essential libraries, something like EE and GEE map. Import GEE map. The next library is the Xarray, because we want to convert the image collection into Xarray formats. So another new library, or one of the newest library, is the XEE library, recently developed by the Google developers and Google, and the XEE allowing us to combine the Xarray format with the Earth Engine image collection formats. That is awesome and revolutionary, and allowing us to bring the satellite data from Earth Engine server into the local server, and then we can apply Python machine learning algorithm on a satellite data that extends our ability in dealing or managing satellite data. So the XEE is not available as a built-in function in the Python, so we need to install it like this. Pip install XEE and import it like this. Let's run a cell, and now we are waiting Colab make a connection to the server first, and the code cell is running now. After a few moments, you can see the libraries importing or installing based on their orders. So when you saw this message successfully installed, then you can clear the outputs. The next step is making a connection between Earth Engine and Colab environment through the EE library. Start with the authentication first, just like this, and then initialize your Earth Engine account. So you need to enter your account ID. If you want to find the associated account ID, just go to the code editor environment. Here in the code editor environment, upper right, there is an icon. Go to the project info and you can find yours Cloud project ID. Copy and paste it into the code, just like this. This is mine, and every user has own actually the project ID. So sounds something wrong with my keyboard, and just a moment, and I wanna actually reset my keyboard to, and then I will continue the tutorial. Sorry for a short delay. Yes, now the problem is solved and I can continue like this. Yeah, sorry for a short interruption. So the next parameter here that is necessary is the OPT URL. If you search on the Google about the Google Earth Engine and XEE, you will find a GitHub page including a detailed instruction about how to use the XEE library, and there are really valuable topics here that offering valuable resources. So now the OPT URL, the second argument for initialize part is available. So now copy and paste into the code, and let's run the cell again. Once the cell is running, there is a pops up and a message pops up and asking you permission to have access to the Earth Engine account. Now the permission is granted, and then we can use the Earth Engine capabilities, functions, and data catalog in the Python and under Python standards. So make a new cell and then identify the region of the interest before further processing. Make a new variable like map. Let's continue with GEE map and map function. So the base map arguments will be set to the satellite and then print the map. After a few moments, you will have a user interface like this that's showing a map with the drawing tools available here that you can select your region of interest without any challenge. So most of the users asking me how to actually find the region of interest using the polygons or the shape files, but it is really easier to use the polygon because drawing tools available here, because it's highly speed up the processing, and most of the time I prefer to do whole of the analysis with the drawing tools and then clip the final result based on a border. So that's what I'm doing in the most of the projects, because as I mentioned, doing process based on the rectangles is really faster compared to the shape files and something like that. So now I'm gonna select a cropland. It is important to select a cropland in this tutorial. I'm gonna select a part of croplands in the northwest of Iran in the Urmia Basin. As you can see, it is located really close to Urmia Lake here, and there are actually several crop fields available here, and I'm gonna select a part of this area as the region of interest in this tutorial. So now this area, for example, looks nice, and also draw a rectangle. I will draw a small rectangle like this. I prefer to select a smaller area because I'm gonna actually have a higher speed of processing during the tutorial, and it is important to able to run really fast and see how the code works first, and then you can apply it for a larger area. And remember that this tutorial is extendable to all around the world, not limited to only one single location. I'm highly suggesting you to use this tutorial for your own region of interest, not the region I'm selecting here, because it allows you to get newer experience and increase your abilities in dealing with the satellite data. If you want to run a code or if you want to actually learn about the Earth engine, the best way is try to use a code for different region and see how it is working from one region to another region. That highly increase your knowledge about the satellite data products and their efficiency in different regions. So now we need to have the rectangle as a variable in the code because we need to bound our satellite data based on the rectangle. So the ROI, a new variable created, sets to from the map, select the last feature, draw last feature, convert it into a geometry like this. Let's print the geometry, and here you will have a polygon with 5 vertices. Okay, now the region of the study area is selected. The next step is about calling satellite data. As I mentioned, there is a product with this name that's actually offering suitable satellite data with Landsat spatial resolution and Sentinel spectral resolution and 3 days temporal frequency. For some areas in higher latitude, it's available in daily, but at least for most of the cases I've tried, it was 3 days frequency. So anyway, but this is really useful for the land cover and agricultural studies, because offering high temporal frequency with a good resolution that we haven't access to such kind of valuable product ever. So now make a new variable, for example satellite collection. So make a tuple and copy the Earth engine snippet into the tuple just like this. And as you can see, we need actually to set the temporal and spatial filters here to bound our satellite data to a specific period of time and a region of interest. Through the filter date, for example, this data limited to 2024, and through the filter bounds, I'm gonna filter this data based on a region of interest. Okay, now let's see how many satellite data available according to these or after applying these filters. 275 elements available in 2024 based on these parameters. And as you can see, for each date that here you can see, we have almost 12 bands, 12 multispectral bands, same as Sentinel-2, offering visible near infrared and shortwave infrared bands that is highly useful for agricultural studies. So as you can see here, for example, you can also discriminate the temporal frequency. This is January 3, January 6, January 8, and it's really good, and the images are really close to each other, and then we can have enough data to monitor the crop condition or their phenological cycles with a good accuracy. So but here we need a function to calculate the NDVI and remove or exclude the cloud cover from the data. Hopefully the F mask layer is available. It's a quality band here, and there are some bits associated with the cloud shadow or something else, and here we can easily use these bits to actually identify and removing the cloud and associated impacts from the satellite data. Okay, now we want to make a function here. A function starts with def. The function name is, for example, the function's name is, for example, index. Each input to the function considered as an IMG. The input will be each collection here. Okay, in the first step, I need to select the F mask layer, for example. So here I'm gonna make a quality QA band sets to from input image. For each date, select the F mask just like this. So the next step, we want to find the bits associated with the cloud cirrus and cloud shadow here. So for example, the first, let's start with cirrus bits set, so it's a kind of the cloud. From QA band, use the bitwise structure. So we want to shift 1 uh, by 0 bits to the left. So, and select all pixels not equal to the 0. This is for cirrus. And the next one, Claude, QA band, again bitwise and so. Then 1 bit left, we want to actually shift number 1 by 1 bit to the left. Again, select the values not equal to the 0. So, and the next bit is bit number 3, cloud shadow. So, here another variable shadow created from QA band dot bitwise and from number 1, the number 1 actually again shifting by 3 bits to the left. Select values not equal to 0. So here we have 3 masks now, one for cirrus, cloud and shadow. So we want to bring them all together in a single variable. So for example, here we will have a final mask sets to get cirrus image dot or. We want to bring them together. That's why or is utilized here. Cloud dot or and shadow, just like this. Okay, the mask, the cloud and associated parameter created. In the next step, we need to calculate the NDVI using band number 8. The band design is same as Sentinel-2. So band number 8 and band number 4 is gonna use to calculate for NDVI for this area. NDVI sets to from the input image get the bands and calculate the normalized difference based on relationship between band number 8 and band number 4, near infrared and the red region of a spectrum. So the band name changed to NDVI, just like this. The function should return one or more results. Here, the index function returning the NDVI as a final result, while it is masked based on a cloud mask created. Mask.not actually turn create an image, a binary image, in which cloud area or cloudy region or shadowy region actually including value number 0, and the rest of the area or clear area will have value number 1. So then copy properties. So we want to have the properties of input to the output. System time start, just like that. So the function is created where the NDVI calculated and all cloud and shadow effects removed from the satellite. Just we need to apply the function on the existing collection. Make a loop structure by map and apply the index. Let's run again. Something's wrong here. Normalized difference. I think there is a typo here. Normalized difference. I think the problem is fixed now. And as you can see, again we will have 275 elements like before, but this time we have only one band, that is NDVI with system time start property that is necessary for time series analysis. Okay, everything's fine by now, and the next step in the next step I'm gonna convert the image collection format into Xarray format. We want to do this process because in the Xarray structure we have access to numerous functions in the Python that can help us for the visualization or machine learning analysis, and it is really easy to calculate the phenological parameters and growing season analysis rather than using own or original functions in the Earth engine. As you know, the original functions or script in the Earth engine are really limited, and most of the time for the advanced analysis you will face with a lot of challenges, and you need to write the heavy code, and it is really difficult for the users. But thanks to the Xarray format and XEE, you can use ready-to-use functions on Xarray structures compared to writing really complicated scripts. And because, as you know, most of the people who are watching this tutorial are not programmers. They are earth scientists, or they are environmental engineer, hydrologist, and they want to know how to deal with the satellite data, and we need to show this as easiest as possible because we are not programmer and we want to learn how to use remote sensing data to extract the information. So now in the next step, let's make a new variable ds from xr library, bring open dataset. So the input collection imported, the next parameter engine sets to the EE, scale sets to 0 point. So the here before the scale we need to address the CRS EPSG 4326. CRS or coordinate system here, the coordinate system ID here is EPSG 4326. This is a unique ID in all around the world if you want to apply WGS84 on your satellite data. In the WGS84, the scale will be based on a degree. For example, 1 degree equals to 100 kilometer. That is really complicated. So it is better to reduce the that's why we need to reduce the scale pixel size to the 30 meters. For example, 0.1 is 10 kilometer, 0.01 is 1 kilometer. So just like this, we can finally reach to the 30 meter by actually a 3 0 before, or 3 0 before 3, just like that. So, and the next parameter, the region of interest, ROI, geometry sets to the ROI. Now I'm waiting for the process. So once the process is done, the data set is ready. As you can see, we have a multi-dimensional structure and no longer image collection is available. In this format, we have an array-based structure, one dimension related to the time, and we have an array of times, we have an array of latitude, an array of longitude, and also there is a variable here in 3 dimension, time, long, and lat. So now in the array-based structure, it is faster and easier to analyze the satellite data, and you can apply several algorithms without writing or without complicated scripting. So that's very useful things. So as you can see, we have, for example, 275 images. Maybe this area covered by couple of frames, or and a couple of frames, or maybe we have a couple of images per day. Such kind of actually complicated situation we have about the times and the temporal frequency in this area. So I prefer to, for example, here I prefer to fill the gaps, existing gaps, using the DS ruling in the first step, and then we can resample it to a regular interval to solve the time related issues and multi-frequent or multi frames per each date. So Now let's start with the DS. First of all, we need to sort the data set based on a time and then based on a time. That's a really important thing because maybe we have actually some disorders about the times, so sorting the or times actually helping us to avoid further errors in the next step. This is necessary, that should be run. We want to make sure the time is in the order and we have no challenge about it anymore. So the next is, as you know, there are some no data on the satellite data here because we already masked the cloud covers. We can fill them by rolling or rolling average technique. So ds roll sets to get the data set and then apply a rolling function. We need a window size. For example, I prefer 10, uh, as long as actually when you have a longer window size or bigger window size actually helping you to fill more uh, no data values or actually offering you more a smoother output. So and time is 10, center is true, and mean periods sets to 1. Calculate the average through the time or median. So let's run. As you can see, the process is done and DS roll actually uh, provided a smooth NDVI through the time, and most of the gaps fill it after applying the rolling. If still you can see some, if you see some sort of no data values in the next step, meaning that you need to increase the time windows in this step. So the next step is about the the next step is about the temporal frequency. As you can see here, we have over 200 satellite data during the growing season. I need to convert it into, for example, 2 weeks frequency. So for example, or 10 days frequency. 10 days. So get the DS roll images, bring it into resample function, and a temporal dimension will be changed to the 10 days. For every 10 days, I need to calculate the NDVI through the time. So the DS with 10 days frequency now is ready, and I have 37 images for whole of the year. Okay, now in this step we can do visualization. Dot NDVI variable selected, plot x-axis sets to longitude dimension, y-axis latitude dimension, call axis time dimension, call wrap sets to, for example, 7. I'm gonna have, for example, 7 maps per each row, and the next color map, a combination of red, yellow, and green. This color typically used for NDVI analysis. And the next is the robust. True. The robust means we want to avoid outlier impact for the visualization. Let's run a cell, and after a few moments you will have a multi-temporal plot that's showing you how NDVI changes in your region of interest. Here you can see the variation from January to December for 2024. Higher values or greener area showing higher vegetation, the higher vegetation or more vegetation density, and lower values or the red area showing that the vegetation is not grown yet or it is cutted, for or it's already cut, for example. Here you can see at the end of the growing season the amount of vegetation decreasing, and at the start of the growing season the NDVI or amount of vegetation cover is increasing. This is the phenological cycle about the NDVI. Maybe you will have, for example, couple of increasing and decreasing during the growing season. It depends on your region of interest and climatological condition. But as you can see, the phenological cycle in this area is like this, but maybe in another region will be different. So it depends and varies from one location to another location. But here I'm gonna show you how to calculate important phenological metrics. For example, if you want to find the peak NDVI value for each pixel, you can do like this. NDVI peak sets to get the 10 days data first and calculate the maximum NDVI through the time. So then we can do the visualization. Select the NDVI and do the visualization. X sets to LON, Y sets to LATS, and robust sets to true, just like this. This is maximum NDVI values or NDVI peak during the growing season for the region of interest. So the next is the NDVI base or the minimum NDVI value during the growing season in the images. The benefit of this tutorial is that we have a high spatio-temporal satellite data, and we can see enough spatial details with a good frequency that's helping us to have access to accurate phenological information through the time. NDVI base, get 10 days data, calculate the mean through the time. So now we want to have NDVI mean. So NDVI base is right. So this is the NDVI base, the lowest amount of vegetation cover in the area. As you can see, some of the areas still amount of vegetation cover is NDVI is greater than 0.3. Maybe these areas that are green through the year, maybe these are orchards and already covered by the trees, and they are evergreen areas. If you have orchard, definitely the amount of NDVI is always high during the growing season. So you can see by calculating this parameter, you will be able to get some important information about the crop conditions and the diversity in the region of interest. The next parameter is the NDVI amplitude. The NDVI amplitude is the difference between peak and base. So NDVI amplitude is the next parameter. NDVI amplitude. So here, as you can see, we can actually get some information about based on the differences between peak and base. That amplitude is really useful to find a threshold for each pixel. Most of the time we are thinking about which threshold should be used for the crop type detection, or which threshold should we use to discriminate between vegetation vegetation after and before the growth situation. So now here the amplitude is very useful. The NDVI threshold in each pixel, based on which threshold we can say the vegetation is growing or not. So get the 20% of the amplitude first, just like this, and add it into the NDVI base. At the end you will have a single image that shows the NDVI threshold for each pixel, that shows after which value we can say, okay, vegetation is growing, or vegetation is decreasing, or vegetation is already harvested. So get the NDVI threshold, and let's run. So you can see the threshold is not unique over the region. For some areas, the threshold value is low. For some areas, the threshold value is high. For example, in the darker areas, if vegetation or NDVI value go beyond zero point 0.2, then we can say, okay, vegetation is growing. But if the NDVI is less than zero point 0.2, we can say, okay, vegetation is not growing yet. And here you can see the zero point 0.2 for the most of these areas highlighted with the red color. Or for example, areas with greater than zero point 0.2 shows the greener area, means that NDVI is growing through the time. So that is really helpful things. So in the next step, I'm gonna find the first date the first day during the growing season NDVI goes beyond the zero point 0.2. So this is a sort of growing season for us. So first of all, we need to find all those pixels greater than their threshold. So above or NDVI above threshold sets to get the NDVI threshold. As you can see in the previous code, actually I have an example that here we need the original image should be compared to the threshold values. So the original image was, or original NDVI is DS for 10 days. In each image, find pixels greater than threshold value. So that will be a binary image at the end. The binary image including 0 and 1, that's as type integer. So let's run. Here we can write a code to highlight how areas looks like. We want to actually see in each date which pixels are greater than identified threshold or less than the threshold. So NDVI above here dot select NDVI band plot x sets to longitude, y sets to latitude, call sets to time, call wrap sets to, for example, 7, and just like this. Let's run. So the output will be a multi-temporal binary image that you can see here. Which areas above the threshold in which dates. In the peak of the growing season, almost all pixels are above their threshold, but at the end or at the start of growing season, the pixels are actually below their threshold. So there it is. So now we want to use this NDVI above to find the first start of growing season, a day of a start growing season, and the date or the end date in the growing season. So SOS, a start of growing season, get the NDVI above first and then select the band NDVI and find the IDX max. The ID is time here and we want to convert it into a day of year, just like this. Let's run. So okay, we want to have the SOS. The SOS will be let me check in the previous email. Yes, the NDVI.dt day of year. Yes, in this case, the first date or first day of a year in which NDVI is greater than a threshold will be the SOS. Let's run. So there is no NDVI band anymore. let's run again. So here you can see an image that each pixel shows the start of growing season. Some areas, for example, growing season start after 120 days. For some areas, growing season starts earlier, or some areas starts later. These are really valuable information and helping us to discriminate different crops based on their crop calendar. So, but this is the start of growing season. The next one will be the end of the growing season. Again, get the NDVI values greater than a threshold or above the threshold, and then this time we want to find the last of the dates. So, in which the time should be a slice of nan. Let me check. It was nan or none. Yes, it's like this. None, none, and -1. The -1 means the last step. So the last step, again, IDX max, the last time, convert it into day of year. So now we want to have EOS, end of season. So as you can see, some areas actually growing season is longer. The end of season is around the end of year, after 300 years, but some areas the growing season is shorter and it will be end actually after 175 days. It varies from one pixel to another pixel. So, and when you have SOS and EOS, the LOS, or the length of growing season, is easily computable in each pixel. Just get a difference between EOS and SOS. So now LOS is run. So, and the LOS here is really valuable things that shows the length of the growing season is varies from one area to another area. Some areas length is around 300 days, but for some areas the length of the growing season is less than 100 days. Maybe it depends on the type of the crops or other parameters. So that definitely the type of crops is really important in this matter. So, and if you want to avoid, maybe for some areas you will face with some negative values during the LOS or length of growing season, because of their because a specific condition, a particular condition in the crop calendar in that area. So that's why if you in this case, to avoid negative values, suggesting to apply this equation from X or var. If we have LOS values lower than 0 or negative value, then their pixel values should be added to 365. Otherwise, for the rest of the pixels, keep the same value. So only here for negative pixel, if there is in your region of interest, if you have negative values, so that makes sense and typically happen. So you need to multiply them to 365, and the rest of the pixel should be keep as like as they are. So now I'm running the code, but nothing changed in my output because I have no negative values in my region of interest. But you can actually avoid negative values if there is some cases in your region of interest. I hope you like this tutorial as much as I did. If you faced with any challenge or if you have any question, you can compare your code with mine. The code link is available below this video in the description box, And if the problem still exists, feel free to reach me out and put your comments on my channel. Please share this tutorial with all remote sensing fans in all around the world. Thank you for your attention.